Hello, welcome back students. This is our second video in our energy unit and I'm going to show you why this energy unit is so great and so wonderful. So let's look at this problem. A car that has approximate mass of 1,000 kilograms is driving at 20 meters per second and goes over a ramp that's angled at 37 degrees with a height of 5 meters. How fast is the car traveling when it hits the ground 15 meters below the end of the ramp? So I'm just going to talk you through how we would have solved the problem with forces and kinematic equations, because we could definitely do that. And then we will solve it using energy. So the old way, so the car is going at a constant velocity. If the driver doesn't let up or press down harder on the gas, the car's going to slow down going up this hill, just like a ball would slow down going up a hill. So what we would have to do is we'd have to draw a free body diagram of the car right here, and then solve for the acceleration of the car, which would be down the ramp. Then we'd have the VI of the car to begin with, and then we'd solve for the VF of the car. And remember that the VF is at an angle. Now you have a projectile motion problem, and then you'd have to find your x and y components of this initial velocity and solve for your x and y components of the final velocity, and then do Pythagorean theorem at the very end to get your final velocity. So several steps and a lot of potential to kind of mess up algebraically along the way, and well, there you go. So, kind of a hairy problem. So let's look at it in the energy point of view. Since there is nothing external pushing the car or holding the car back, we're just going to kind of have it at an even, pressing the gas evenly the whole time. Pretend it could be a ball just rolling and going up a ramp and falling. We're going to look at the energy. Our total energy bucket each time will be the same because it's conservation of energy. Energy is conserved. So the easiest way for potential energy to deal with potential energy, since it's mgy, is to choose the lowest point that your object will be and call that your 0 point. So right here's our lowest, so this will be 0 meters. Right here, the car is at 10 meters because the whole thing's 15. So the car right here is actually at 10 meters. Even though it's on the ground, it's 10 meters above the 0 point right there. So we can solve for potential energy because it's mgy. So mass is 1,000, g is 10, and y is 10. So 1,000 times 100 is 100,000. So we get some energy juice there, and we could solve for the kinetic energy because it's 1/2 mv squared. So we have 1/2, we have the mass again, and we have the v right here, 20 meters per second squared. We could add these two. This ends up being, I believe, about 200,000 joules, and this one is 100,000 joules. So the total energy is approximately 300,000 joules. Since the energy does not change, the energy is the same at all three spots. We can look at this middle spot. We don't have to, but we can, and we can say, okay, so the potential energy goes up because the car gets higher. So the potential energy goes up, kinetic energy goes down. So the energy juice sloshes between these two buckets here. Some kinetic energy went to the potential energy on the side. But the total energy, the total amount of juice stayed the same. So on the bottom, our potential energy is 0 because we're at the bottom. So everything is in the kinetic energy bucket. So we know that our total energy was 300,000 joules, and this is equal to 1/2 mv squared. So now we have the mass, which is 1,000, and 1/2 of this, so it's 1 150 square root of 150 meters per second equals V. That is so much easier than the first way I showed you. So this is one of the powerful, wonderful tools of energy, and we're going to get to practice with this quite a lot. Okay, well, I'll see you in the next video.